let's look at those 3 pages. For tomorrow's test, make sure you bring a pen, a pencil, your own ruler, and a protractor and your calculator, okay? All right, let's start on page 11. These are all about these graphs over here. Letter A, that horizontal line means something is not moving. Graph B means that diagonal line indicates that we have a constant velocity. Those are on tomorrow's test. Position time graphs that are horizontal or diagonal lines are on tomorrow's test. This is the only new one. Letter C, if you have a curve on a position time graph, that means the object's accelerating or changing velocity. Letter D, a gradual sloped line means you're moving with a slow constant velocity. If it's a steep slope, that means you have a fast constant velocity. So the only new one here is that curve, letter C. Otherwise, A, B, D, and E, you should have known from Unit 2, will appear on tomorrow's test. Number 2, we're looking at this position time graph. The objects which are at rest are graphs A and E. We know that because they're horizontal lines. Which object or objects are accelerating? It's only D because that's the only curve on the graph. Letter C, which objects are not moving? Not moving is at rest, so it's graphs A and E. D, which objects are changing direction? None of them. They're all moving in one direction. Letter E, which object is going the fastest? That is letter B, and that's because that is the steepest graph that's there. Letter F, which moving object is going the slowest? That's letter D. D is the most gradual slope there is. And G, which objects are moving in the same direction as object B? Well, object B is going in the positive direction. The only other graph that's going up is graph D, positive direction. Number 3, now let's look at velocity time graphs. The only one that you're going to see on tomorrow's test are horizontal lines. Horizontal lines mean that you have a constant velocity. That means there's no acceleration. If you have a diagonal line, that means you're accelerating. If it's a gradual slope line, that's a small acceleration, and a steep slope would indicate a large acceleration. So you're not going to see any diagonal lines on velocity time graphs tomorrow. I might ask you about one, but that's a wrong choice to pick. Everything would be horizontal tomorrow. Number 4, let's talk about these graphs for velocity time. The objects which are at rest are graphs B and C, but that's only at the times when they are crossing the time axis. So right there and right there is when they are at rest. Everywhere else, they're moving. That's a velocity of 0. 0 velocity means you're not moving. Letter B, which objects are accelerating? Those would be diagonal lines. Which graphs have a diagonal line or a portion that's a diagonal line? That's graphs B, C, and D. But D is only in this section right here that's accelerating. Which objects are not moving? Graphs B and C again, but only when they cross the time axis. At those 2 points, there's no motion. Letter D, which objects change direction? Changing direction means it goes from the top part of the graph to the bottom part, quadrant 1 to 4 or 4 to 1. They cross the time axis. That's graphs B and C again. Letter E, which accelerating object has the smallest acceleration? That means we're looking for the shallowest diagonal line. That would be graph B. Letter F, which object has the greatest acceleration? That means which one is the steepest? That's graphs C and D. D, but only in this section, this diagonal component is parallel to that, so they have the same large acceleration. And letter G, which objects are moving in the same direction as object E? Object E is moving in the negative direction because it's down in quadrant 4. So the other graphs which are down there are graphs B, C, and D. But C only in this section. And B only in this section for that period of time. Any questions on page 11? All right, let's go to page 12. Now let's look at these 5 position time graphs. Graph E goes with 5A. Graph B goes with 5B. Part C is graph D. Part D is graph A. Part E is graph C. All right, number 6 and 7, you had to draw ticker tapes for these graphs here. So if I were to describe in words what's happening, A is moving to the right and slowing down. B is going to the right, but speeding up. C is going to the left and speeding up. D is going to the left and slowing down. So how do I represent that? A should look like this ticker tape with an arrow above it to show we're going right, with the dots getting closer and closer and closer together. B, arrow to the right to show we're moving right. The dots get further and further and further apart. C, arrow to the left. We're now going left, and the dots should get further and further apart. D, arrow to the left because we're traveling leftwards, negative direction. These dots get closer and closer together as we move in that direction. Number 7, let's go through the descriptions of motion. A is moving to the right and speeding up. B is going to the right but slowing down. C is going to the left and slowing down. D is going to the left and speeding up. If I were to draw that on a ticker tape, A, the ticker tape should start close together and get further and further apart with the arrow to the right. B needs an arrow to the right, but the dots get closer and closer together. C, arrow to the left, and as I read them to the left, they should be getting closer and closer together. And D, arrow to the left, and they should be getting further and further apart. All right, any questions on page 12? All right, let's look at the last page of the homework, page 13. The first 2 will be on tomorrow's test. Constant velocity in the positive direction. The direction you're moving in is the direction of your velocity, positive. A constant velocity as you go to the right, we should have a positive slope diagonal line. Doesn't matter where this diagonal line starts. You need a positively sloped diagonal line. Velocity time graph has to be up in quadrant 1, that's horizontal. The second one, now you're just going in the negative direction, which means your velocity is negative. Constant velocity means we need a diagonal line with a negative slope. Doesn't matter if it starts at the origin or above it or below it. Just a negative slope diagonal line on the position time graph and a horizontal line on the velocity time graph, but below the time axis. Those are on tomorrow's test. These are the new ones for today's quiz. When you have a positive direction and a positive acceleration, that means your velocity is positive. The positive direction is your velocity. And when the velocity and the acceleration are the same direction, both positive, you're speeding up. So on a position time graph, we need a parabola that goes up and gets steeper. The velocity time graph is a diagonal line with a positive slope, and it must be above the time axis. It can't start below the time axis. That would mean it was going left. It's not. It's going in the positive direction. Negative direction with a positive acceleration, our velocity is negative due to the negative direction. The positive acceleration is opposite sign of the velocity, so that means you're slowing down. Opposites indicate slowing down. So our position time graph needs to go down because we're moving in the negative direction, and since we're slowing down, it levels off. It gets shallower. The velocity time graph has to be below the time axis, negative direction, and its speed must approach 0. So it's a diagonal line with a positive slope. Positive slope is positive acceleration here. If I look at the negative direction and negative acceleration, my velocity is negative. These are the same sign, so I'm speeding up. My position time graph has to go down. That's our negative direction, but it must get steeper because we're speeding up. The velocity time graph must be down below the time axis, a diagonal line with a negative slope. And our final one, positive direction, negative acceleration. So our velocity is positive, but since they are opposite sign, we're slowing down. So our position time graph should be going up, but getting shallower to indicate we're slowing down. And our velocity time graph's in the positive quadrant, quadrant 1, diagonal line with a negative slope. Negative slope is negative acceleration on that type of graph. All right, any questions? Okay, you're going to use those 3 pages to help you with today's quiz. So go ahead, pull out your Chromebook now, and you can go ahead and take the Unit 3B quiz on the graphs for accelerated motion. While you're doing that, I'll hand back your test corrections from Unit 1. Okay, I think everybody's done with their quiz, right? Okay, so now let's take out your Unit 2 packet and that trig review worksheet that I asked you to finish up for homework. There were 2 questions on the video that I didn't get to go over with you, and I asked you to finish those up for homework. That was on Friday's assignment. So we'll hopefully get a chance to look at both of those additional questions. I think it was problems 5 and 6. Does that sound right? Okay. So hopefully we'll get to go over those. But I want to start on page 28 in your Unit 2 packet. That starts with this Unit 2 Worksheet 5 page to go over that. For tomorrow's test, as I mentioned, please make sure you bring a pen, a pencil, a ruler, a protractor, and your scientific or graphing calculator. Tomorrow's plan is this. We are going to start period 8 with a lab. It's a review of some additional stuff from Unit 2. So I don't feel too bad doing it first. I want to do it because it's review. It's stuff that would be on your test the following period. So we're going to do that first, period 8, and then period 9 we'll take the test. Sound good? Still for the test, and the lab, this is all you need to bring. You don't need all your physics stuff. Okay, just those items are necessary for tomorrow's class. Okie doke. Let's get started on that page 28. I'll go over everything, and as you have questions, just feel free to shout them out, and I'll try to help you out as we go. Okay, so this was the graph I gave you, and there are 3 segments to it. So what I do is I number them, so that way I'm consistent across the board. So segment 1 on a velocity time graph should be a horizontal line up in the positive quadrant, and relatively, it doesn't have to be super close because it's moving pretty quick, but it is slower than what it's doing in number 3. So number 3's horizontal line is further from the time axis, but it's negative slope, so that means it's down the negative quadrant. Number 2 should be a velocity of 0 the whole time because that's a 0 slope. So we have 3 horizontal line segments, 1, 2, and 3, where 3 is a little bit further away than 1 is. So my descriptions of motion, segment 1 is traveling to the right with a slow constant velocity or constant speed. Number 2 is stopped or not moving or at rest. And number 3 is going left at a fast constant velocity or fast constant speed. The motion map, I'm not going to ask you to draw a motion map tomorrow, but I could ask you to draw ticker tapes. So the ticker tape diagrams are a little easier because I don't have to worry about the arrows. You just have to place the dots in the appropriate places. So what we see on this motion map, there are no times anywhere, no specific numbers. So we can't put, doesn't matter whether you did this in 5 dots or 3 dots. But I should see arrows to the right, then several stacked, and then arrows to the left. And the arrows to the left should be longer than the ones going to the right. All right, next graph. I gave you this velocity time graph. Again, I'm numbering the segments 1, 2, and 3. Segment 1 should be a steep negative slope diagonal line. Number 2 should be a shallow positive slope diagonal line. And 3 is a horizontal line. So now, what does line 1 mean? Line 1 is traveling to the left with a fast constant speed or velocity. Number 2 is traveling to the right with a slow constant speed or slow constant velocity. And number 3 is not moving. It's at rest. So again, the motion map, number of dots doesn't matter, but I should see arrows to the left that are longer than the arrows to the right, and then several dots stacked to show no motion. Okay, the next one. This was the graph I gave you, segment 1, 2, and 3. 1 should be a horizontal line in the negative quadrant, but fairly close to the time axis. Number 2 on the velocity graph should be on the 0 velocity value on the time axis. And 3 should be far away from the time axis in the negative quadrant. So 1 is traveling to the left with a slow constant velocity or speed. 2 is not moving, and 3 is also going left, but with a fast constant velocity or fast constant speed. So my motion map should show arrows to the left. They're same size as each other, but small. Then no motion, dots stacked. And then arrows to the left, all the same size, but these are all longer than those were. Last one on page 28. What did I give you? I think I gave you the velocity time graph, line segment 1, 2, and 3. So line 1 on the position time graph should be a horizontal line. 2 should be a diagonal line with a positive slope, fairly steep. And 3 should be a diagonal line with a negative slope, fairly shallow. Number 1 is not moving. 2 is going to the right with a fast constant velocity. And 3 is going to the left with a slow constant speed or velocity. So our motion map should show several dots stacked, showing no motion, then arrows to the right, which are fairly long, and then arrows to the left, which are shorter. Any questions on page 28? All right, let's go to page 29. Now I'm giving you times. So we should have times on our graphs. So our position time graph should start at the origin with a positive slope diagonal line. The peak of that graph should be at 4 seconds. Then we should have a horizontal line segment that ends at 6 seconds. And then a negative slope diagonal line back to the origin, or the zero position rather, at 8 seconds. So on a velocity time graph, I see 3 horizontal line segments, positive, 0, and negative, where the positive is fairly close to the time axis, and the one from 6 to 8 seconds is much further away, below the time axis. The 4 to 6 is on the time axis. Now our motion map, we should have these number of dots to get us to 8 seconds. Starting here at 0 seconds, traveling to the right, I should see 4 arrows with this length. And then they're stacked, and then arrows to the left, which are much bigger. The starting and ending dots should line up with each other to show that we are back at our initial position. Again, are you going to have to draw this tomorrow? Now. Next one. What did I give you? I gave you this motion map. So if I put the times on there, 0, 1, 2, 3, 4, 5, 6, 7 seconds worth of travel. So my position time graph starts at a particular position to the right of the origin. The origin would be on the left side. So this is starting to the right of the origin. It's going left, so negative slope, then a horizontal line, and then a positive slope diagonal line, and that ending point should be at the same vertical height as this point here. So we are at the same position starting and ending. If I put time values, this is 0 seconds. That point there is 2 seconds. This is 4 seconds, and that is 7 seconds. So my velocity time graph has 3 horizontal lines, a negative one, a 0 value, and a positive value. This negative one is faster than this one here because we're traveling the same distance here, but in more time. So you're going slower. That's why it's closer to the time axis. So the description, we have an object traveling to the left with a constant speed for 2 seconds. It then stops for 2 seconds, and then it moves to the right with a constant speed for 4 seconds, and it returns back to its initial position. All right, next one. We gave you the description. So object A starts 10 meters to the right of the origin. So that's a positive 10-meter value on the y-intercept. It's traveling to the right. It's traveling to the left. That means a negative slope, and the slope has a value of 2 meters per second, but it's a negative 2 meters per second. B starts at the origin. So its y-intercept should be 0 meters. It's traveling to the right, so I need a positive diagonal line, but the slope there is positive 3 meters per second. So since this slope is a larger value than that, this should be steeper than that one. On my velocity time graph, B has a y-intercept of positive 3 meters per second, and A has a y-intercept of negative 2 meters per second, and they're both horizontal lines. And here's my motion map. A is starting at a position of 10 meters with arrows to the left, which are 2 meters per second in length. And B is starting at the 0 meter position with arrows to the right, which are 3 meters per second of length. So these should be longer than those. All right, the last one. I showed you this. Do you see how A is starting at the origin, but B is starting to the right of the origin? So that means A's diagonal line with a positive slope starts at 0. B's diagonal line with positive slope starts ahead of it at a positive value. But do you notice how all those arrows are the same length, all of them? That means they have the same speeds. So these lines are parallel to each other. On my velocity time graph, it's just really one line, but it's the same line for A and B up in the positive quadrant. And my description, A is starting at the origin, moving to the right at a constant speed. B starts to the right of the origin, moving to the right, and it's moving at the same constant speed that A is. Any questions on those 2 pages? 28 or 29? All right, let's go to 30. With this position time graph, I want you to find the average velocity. The velocity is the slope of that line. So you're going to do the displacement over the time or the rise over the run. So I found the rise. The rise is positive 50 meters divided by 6 seconds, the run. Now, based on the values here, I'm only going to get 1 sig fig. So my answer gets rounded to 8 meters per second. And I do need a sign on it because it's velocity, not speed. It's a vector. So it's positive 8 meters per second. Now, the equation for this graph, y is mx plus b, but we change everything. On the y-axis, I have position. The slope is the positive 8 meters per second I just found. The x is the variable named time, and the y-intercept is positive 10 meters. So position is positive 8 meters per second times time plus 10 meters. All right, let's look at this velocity graph in 2A, the descriptions. From 0 to 2 seconds, the object is traveling to the right with a constant velocity of positive 4 meters per second. From 2 to 3 seconds, it's traveling to the left with a constant velocity of negative 3 meters per second. And from 3 to 5 seconds, it's not moving. It's at rest. Now, draw the position time graph and number the x-axis. So those are your times. So here are the positions, and there are the times. So at 0 seconds, we're starting at the origin. We need a slope of positive 4 meters per second, and that ends at 2 seconds. Then I need a negative slope of 3 meters per second, which ends at 3 seconds. And then I need a horizontal line from 3 to 5 seconds. Now, let's answer the question. C, how far does it travel from 1 to 2 seconds? How far is distance? So I'm going to use speed is distance over time. So the distance is the speed times the time. The speed between 1 and 2 seconds is the 4 meter per second. Between 1 and 2 seconds is only 1 second. So it's moving 4 meters between 1 and 2 seconds. Now, what's the total displacement? These answers now are going to help me get the values on my y-axis. So from 0 to 2 seconds, I find the displacement by doing the velocity, positive 4 meters per second, and multiplying by 2 seconds. So it moved positive 8 meters. The displacement in the next segment would be negative 3 meters per second times 1 second, or negative 3 meters. And finally, in this horizontal line, it's not moving. 0 meters per second times 2 seconds is 0 meters. So the total displacement, if I add these up, is positive 5 meters or 5 meters to the right. Now, how do I get these values? I know I was assuming it started at the origin. I then end up 8 meters to the right of the origin. So that's why this position is now 8 meters. I then have to back up 3 meters in the next segment. So 8 minus 3 is 5. That's why that coordinate is now 5 meters. And I stay there for the next 2 seconds. Any questions on that page? All righty, let's go to the last page, some guess method stuff. Number 3, I want you to find the average speed in part A. So we use speed is distance divided by time. Distance is not a vector, so I don't care in what direction. Johnny went 1,920 miles out to Wisconsin and back. So we add those up. He did 32 hours out, 32 hours back. That's why I'm adding everything. Gives me a total distance traveled of 3,840 miles in 64 hours. Sig figs. 64 hours has 2 sig figs. The numerator has 3. So I must round my answer to 2 sig figs, 60 miles per hour. If you just said 60 miles per hour tomorrow, you would lose a point for sig figs on that question. Letter B, find the average velocity. Average velocity is the displacement over the time. So the displacement is 1,920 miles out plus negative 1,920 miles. Why is that negative? Because he went backwards. He returned to his starting point. So the total displacement is 0 miles. 0 because his start and end positions are the same. Same 64 hours of total travel. gives you 0 miles per hour for the average velocity. So compare these. The velocity is 0 because he wasn't displaced. That's really what that means. All right, let's look at the velocity time graph here. Describe the motion. Line segment 1 is an object traveling to the right with a fast constant velocity. 2 is going to the left with a slow constant velocity. Don't worry about the motion map in part B, but this is what it would look like if you did it. Okay, number 5, guess method. The speed v is 95 meters per second. The time t is 12.5 seconds. The unknown is d, distance. How far is distance? So we're going to use the equation. Speed is distance over time. So the distance is speed times time. Now we're going to plug in 95 meters per second times 12.5 seconds. We're going to get an answer with 2 sig figs because of the 95. Round your answer correctly, you get 1,200 meters. Now, dimensional analysis. D is VT. You check the equation you plugged into. What was the speed measured in? Meters per second. What was the time measured in? Seconds. The seconds cancel, leaving us with meters, which is what I got for my answer, so that checks. All right, any questions on the packet? All right, let's go to the trig review worksheet. Questions 5 and 6. All right, first thing you should have done in number 5 is sketched it out. 60 meters west is left, 80 meters south is down. So the displacement is that side of the right triangle with the arrow pointing down and left. So the first thing I'm going to do is I'm going to find the magnitude of the displacement using Pythag. A squared plus b squared equals c squared. I'm then going to plug in. So the magnitude of the displacement is the square root of 60 point meters squared plus 80 point meters squared. So when I work that out, I get 100 point meters. Keeping the precision, this is what we call vector addition. And remember, the rule for addition is precision. These went to the ones place. See how there's a decimal point after the 0? That means I have to put a decimal point there. Otherwise, it would be marked wrong. Now, first thing I'm going to do now for direction is come up with the inside angle using the alpha is the inverse tan of the opposite over the adjacent, which in this case is the y value over the x value. So I'm going to plug in inverse tan of 80 point meters over 60 point meters. So we find that the angle inside the triangle is 53 degrees. But this is in quadrant 3, which means that our answer is between 180 and 270. And my 180 degrees is from here to here. I have to go beyond that by the amount we just found. So I'm going to add 180 to the 53 degrees. Make sure you include these degree symbols, please. Those are the units. That gives us 233 degrees. So my final answer is that the displacement is 100 point meters, comma, 233 degrees. And the last one, let's start with our sketch. It should look like this. 9 meters east is an arrow to the right, and then an arrow going down, which is 12 meters to the south. I'm looking for that arrow. I need an arrowhead on it. Displacement, down and right. So let's get the magnitude of the displacement using Pythagorean theorem. A squared plus b squared equals c squared. So I'm going to do the square root of 9 meters, that amount squared, plus 12 meters, that amount squared, gives us 15 meters. Again, I'm keeping the precision. These went to the ones place, so that has to go to the ones place. Round it to the ones place. Now I'm going to come up with the inside angle there using the inverse tan of the opposite over the adjacent side, which is the y value over the x value. So it's the inverse tan of 12 meters over 9 meters. That gave me 53 degrees here also. Now, if I look at this picture, the direction I need is from here around to there. The angle I need plus the one I found make a full circle, 360 degrees. So I'm going to back up by that 53 degrees, which means I'm going to subtract 53 degrees, giving me 307 degrees. So my final answer is 15 meters, comma, 307 degrees. Ashley? So I look at which way it's pointing into which quadrant, right? So this one's going into quadrant 3, down and left. So that's 180 is left and 270 is down. So my answer has to be between 180 and 270. And then what I try to do, remember, we always start at the positive x and go around the origin counterclockwise. So the one I'm finding is that little piece of the big arc. And you see how that top half of that arc is 180? So that's why I have to go beyond it and add it to 180. Where in this case, again, starting at the positive x, go around the origin counterclockwise gets you to there. The one you're finding inside the triangle is this piece. But this would be 360 pointing to the right. 0 and 360 are the same angle. So I have to go backwards by that 53 to get me to where I'm ending up. That's why I'm subtracting that from 360. Does that make sense? Mm-hmm. And this one's quadrant 4 because it's pointing down and right. So it should be between 270 and 360. But the angle I found is inside the triangle. If I had found it out here, then I would add it to 270 because 270 would have been the vertical. But it's not. It's with the horizontal, so that's why I'm backing it up. Okay. Anything else? So tomorrow's test, I can tell you right now, you're going to have one problem similar in style to these that are on the front. You're going to have one problem similar in style to one of these on the back. And then you're going to have all these graphs, verbal descriptions, ticker tapes, guess method problems. That's unit 2. There is no accelerated motion. So if you see something that says acceleration, guess what? It's wrong, not it. It's all constant velocity or not moving. And like I said, we will do the test period 9. So that way we have period 8 to do some review with a physical lab. Okay? Sound good? Okay.
When it comes to like these types of questions, will it say like you student opportunities?
Yeah, or it will say calculate versus draw.